Our first speaker is Dr. Sarvenaz, Choobdar, and she's a data scientist working at the University of Lausanne, and she's specializing in computational biology. And she did her PhD in University Porto in computer science, where she was working on complex network analysis. And after this, she was, during this, she was already visiting PhD at EPFL. And what really impressed me about her, she is a really active educator, a voluntary worker, and she is working with power coders on providing software, like coding power to refugees. She is one of the organizers of Our Ladies, and I asked her specifically to talk about this during her talk. And you can learn a little bit about this. And also the Django Gears, which is it's an organization which is providing one-day events for women, so to learn them to code, and I don't know which language or.
It's a Python.
Okay, yeah. So, and Our Ladies is, but I know that men can also come for.
Yes.
Yeah. So. So.
Thanks, Pavel, for the introduction. It's a really great pleasure to be here and give a talk in machine learning community in Lausanne. Before starting, I really like to thank Pavel and his colleague in organizing this series of talks. It's really great opportunity, I think, for all of us to hear about the recent work in the field without really having to travel to some conference or somewhere to just hear some nice talk. It's really great opportunity. Today, I'd like to talk about the Dream Challenge we organized for module identification in genomic networks at the Department of Computational Biology in the University of Lausanne. First I would like to give you some background about the biological perspective of the work, and then I will go to more machine learning and how we did it. So basically in biology, we know that for most of the complex traits like height or eye color or cancer diseases, not one single gene is involved. So when you do the genome sequencing, finding association with one single gene to the disease doesn't tell you much. You need to find group of the gene that collectively affect the phenotypic level and derive this problem. So basically this issue is studied under the topic of biological pathway and module identification in biology community. The common way is that people go to the curated annotation database that are available online and download the kind of annotation that they are interested in it, like Go categories or biological processes. And then they look at their omic data and see which genes are similarly co-expressed or differently expressed across different tissue or samples or cohort, and then see if this group of the genes that they get from their omic data show any enrichment for the annotation that they have from database. An alternative approach to it is using network analysis. Basically, instead of just focusing on one annotation, the idea is that to leverage all information that you can get from the all omic data instead of just filtering a priori your omics data. So basically, the pipeline is like getting your omic data, building some networks from the omic data, like gene co-expression networks, will give you a network that the objects are the nodes and the connection tells how similar genes are expressed across different conditions. And then the task is to apply some modularization algorithm and get your group of the genes and then look at their annotation from any database. This this approach has some advantages over the other one. Mainly gives you the opportunity of finding a new pathway or or extending the known pathway instead of focusing what is already known in the community. And also it gives you a advantage of leveraging all the omics data that are at larger scale nowadays are available, and it's a great opportunity to take advantage of them. The main thing of this pipeline is that how we can best do this modularization, like finding group of the module, group of the genes, from the network that we build from omic data. And this is a problem that is kind of classical, or we can say in the network science, that it's been studied for years and years and has application in other domains like social networks or other type of the network structures. So why we have to invent a wheel from beginning in biology? We can just use what is developed in the other field and adapt. But the issue is that these methods are like many hundreds of the modular identification algorithms are out there, and really understanding which one is relevant for the biological network and which one of them perform well by a research group, if it's possible, is not really wouldn't be rigorous and comprehensive. So we thought that we can do it with the help of the community, like asking the crowd, the community out there, all the machine learning people and all the group that works specifically on this network science to help us with answering this problem and solving this problem, where we provide the context, the biology context, and they help us with the machine learning algorithm, which it's their skill and not biology, not biologist. From the other side, we have the reproducibility problem in every discipline in the research and academia, including biomedical. Basically, everyone published some paper somewhere and they claim their result is good and the method performed this % better than the other. But we all know that very few % of all these researches are actually reproducible, or even if the code and data are available. And there are several issues that in academia and research we all are kind of familiar, and we know these are the problems. First of all, that who has the data can win. Basically, who has the money to gather as much as data that they can. Basically, they can run any algorithm on it, and we know that nowadays the algorithms are pretty good, and if you give enough data to them, they can perform quite well. So if they have the money to generate all the data, they win in the field. So this is not fair, and these people don't share the data usually. And the other problem that we are all have is kind of the self-assessment that we do. Okay, some team develop an algorithm, they compare it to some baseline. This baseline could be something that is widely used in the field, but not necessarily the best algorithm in the field. But anyway, because you want to get published, you have to compare yourself to that widely accepted algorithm, and not necessarily the best one. And the third problem is that, okay, if you have the money to gather the data, you just apply some method on it, and you are the first one to publish in that field. And since you are the first one that publish in that field, you get to publish in the good journal, and anyone else that wants to do some work in that line, they have to cite you because you were the first one, so it's going to be all the time citing your paper, and because your citation goes high, so it's become a kind of a method that, okay, is the best, so everyone should use it. But we will see in this challenge that not necessarily it is a valid thing. But with the open data challenge, we can kind of address all these issues. We made the data publicly available, so everyone has this chance to try their method. So it's more fair competition, more fair game. And we have the opportunity of applying many more methods. And the evaluation, of course, is much more fair. We have a kind of blinded evaluation that ground truth is not revealed to the people. There's the organizer that basically know more about the ground truth. So it's more fair game than what is usually done in research. So basically, with the open data challenges like the one we organize, we can make the data available, so we share the data with everyone, so everyone has the opportunity to contribute, and we have the chance of objectively assess all the method, not focusing on one or two or some more well-known method. And at the end, we have this chance of building a collaborative community around the topic data and finding the best method that actually works best. Having all this said, we designed a dream challenge, which is basically a crowdsourced competition for computational biology. It started in 2006 at the IBM Research and Sage Bio Networks, and this is a kind of organization that wide range of challenges in system biology, precision medicine, cancer research, and sequencing data analysis are organized there. And nowadays in computational biology is kind of very well known. It's like a Kaggle or KDD competition in machine learning community. So we designed our challenge and proposed to the DREAM community, and we were lucky to be accepted. So we launched our challenge in summer 2006, and until October the same year, the challenge was running. So the people could come and subscribe for the challenge, get the access to the data, work on it, and we had like 400 participants that registered. We had lots of communication going on the platform, the challenge platform, discussion around some design of the challenge or data pre-processing. It was really great collaborative work, even in the preparing the data before releasing and before launching the actual challenge. And I can see it was quite successful because we had a good number of the people that participated at the end and contributed methodology. Here I would like to give you an overview of the design of the challenge that we designed. Basically, we gathered 6 different types of the biological network, like protein interaction, signaling network, co-expression, cancer, co-dependency, and homology network and these networks come from different type, like all of them is the semantic between the gene, but from different perspective of biology. And of different, of course, size, and some of them are weighted, some of them directed, so very diverse collection of the network. And we designed 2 sub-challenges. So basically, first we wanted to know what are the modules in single network. So in each of these networks, we asked the participant to modularize each network separately. The sub-challenge 2 is a kind of multi-network module identification, where the assumption was that, okay, if we kind of merge the information across this type of the network, can we leverage it? So basically, because they are all genes and the connection is the different type of relation between the genes, the idea was that, okay, if we allow kind of sharing information across the network, we were thinking that it could help. So basically, we asked them to do the prediction in these 2 different settings, and then we had different kind of data set that is kind of orthogonal to how the network is built, which is based on Genome-Wide association studies that I will tell you more in the following slide. And then we check the association of the module with the disease. So basically, when one module is predicted and it says this group of the gene is one module from this network, we check how many of the genes in this module are associated with a particular trait. And if it's many of them more than random are associated, we call it a trait module. And the scoring is based on how many of these modules a team can predict. Okay, as I said, we set up a platform that people could access the data, read about the instruction, how data can be accessed, and all these details. And then we had and to submit the result, and we had a scoring pipeline that we implemented on the computing clustering clusters of the SIB, which is the Swiss Bioinformatics Institute. And because we had large number of genome-wide association studies, 6 networks, many submissions, so we needed really parallel processing pipeline that can handle all these number of submission and record back the scores to the leader, so that in the training phase they can tune their method and work with the different parameters that their method has. So more detail about the network that we had. If we go to the detail of this network, I should mention that at the time of this challenge, none of these networks were published. So these are all unpublished data. And when we made it available to the participant, it was the anonymized version. So basically, they wouldn't know what are the genes. So no biological context would have been used for modularization. It's all about network topology and nothing else. About the module assessment, so we receive a group of the genes that the a team predict is a module, and we want to know if it's a disease module, if it's associated with some disease or not, or some trait or not. This we use genome-wide association study. The genome-wide association study use the sequencing data, like if you get the genome of the people and a large cohort, you check if the single position in the genome, variation in the single position in the genome is kind of associated to a particular trait or not. So we have such a study for 200 different diseases from different categories like psychiatric, blood lipid, cardiovascular trait, all these, and we checked if each of the predicted module have enough number of gene in it that has a variant on it that from GWAS association is a trait SNP. So this is a kind of a statistical pipeline for this scoring. So basically, from the GWAS genome-wide association study, we have a reference population that tells us what is the variation, and then we have for different trait what is the variation for different trait, and we get a kind of a p-value scoring for that, and then we aggregate the SNP, single nucleotide polymorphism p-value to the gene scoring level, which tells us if that gene is associated with one trait or not, and then we aggregate this gene scoring to the module level that tells us if the module is associated to the trait or not. So we had two phases of in our challenge, of course, a learning phase that the team could work with their method, and they had each 20 submission, and we did an evaluation with 76 GWAS from 76 trait, and they had only one submission for the final round, which based on what we scored them and we ranked the team. And of course, the evaluation was on the different GWAS dataset. At the end, in the final round, we received 42 different methodology. So basically, out of all 400 team, only 42 of them submitted some prediction at the final round. And if we look at their methodology and the pipeline that they use for the prediction of this module, no matter how they perform, we can kind of categorize them in these 5 categories. So first group is the kernel clustering algorithm that basically they transform the adjacency matrix of the network to a new similarity matrix. So they have a kind of kernel that transform this gene relation to a new dimension, and then they modularize this new similarity matrix. The other category is the optimization algorithm. Basically, they try optimize modularity by some heuristic algorithm like a Lausanne or like Markov clustering, that they try to find a group of the gene that give the best modularity overall for the group of the predictions. And the third category are the random walk based that start with some seed, and they expand the group by doing random walk over the network and finding group of the genes by random walk process. And the fourth category is a seed expansion. It's a kind of agglomerative process that again start with some random seed and extending the seed by adding more gene to the seed, so that they have more connection between them comparing to the gene in the other seed set. And the last category is the Ensembl Method, which kind of is a aggregating method. So basically what they did there is they apply several different modularization algorithms, and at the end they do a voting on it that tells you the grouping of the gene that comes from the consensus of these methods. And if we look at the distribution, basically random walk-based and modularity optimization were the most popular type of the algorithm that teams used. And if we look at their score, basically here we have the score of these 42 group, and they are grouped by their category. Our best team comes from the kernel clustering category, but we can see that not all the top 3 comes from the same category. Basically, any of these category could perform quite well. What makes them really performing well is not only the method, but is more the pre-processing step. If you look at their methodology and the code and the write-up that they submit, you can see that what makes this algorithm like this one better than this one is the pre-processing step and how they handle the noisy connection and redundancy in the network. So that makes this, for example, random walk-based better than the other one. And if you look at the contribution of the network to the trait module, like the predicted module that are associated with some trait, you can see the signaling network that we had has the highest number of the module predicted. And when we go and look at this network, again, this is the smallest network and the cleanest network, which is basically very curated, and all the connections are less noisy than the other networks, like first PPI. This is a string network. Maybe many of you know it. It's kind of automated generated network. If I want to give you a summary about our best performing team, so basically they were a team from Tusk University in the US, and the cool thing about them is that their method was not one of the off-the-shelf methodology like Lausanne, Markov clustering or something. They developed this algorithm and they had publication on it. This double spectral approach, the general idea is that, okay, the similarity of between the object in the network, basically 2 genes, if you want to measure the similarity of 2 genes, it's important to avoid highly connected genes. Basically, one gene that is like this one that is connected to many other genes, it means that it's involved in many biological function, which doesn't tell you necessarily, if you go a connection like this, it doesn't tell you these 2 categories are similar. So you should avoid finding distance between yellow node to green node through the hubs, because this is not necessarily similar gene to this one. So, and I think it's more easier to understand if I give you an example on the social network. So basically, people that are connected to celebrities are not necessarily of the same type. So, but people that are in my social network are more similar or homogeneous people, because for the celebrity you can find wide range of people, while through me more homogeneous people are connected and like a smaller ego network form. So the same idea applies for the gene network. So basically, with this idea, they built this kernel function that transformed the adjacency matrix to a new adjacency matrix with getting rid of the hubs and finding the similarity without using the hub for measuring the distance. And then once they do this, they apply spectral clustering, which is a kind of standard modularization algorithm to find the group of the genes in the networks. And the cool thing about this method, again, is that they don't do any pre-processing before applying the kernel. So the kernel is powerful enough to get rid of all the noise and redundancy. So it was also interesting. And the other thing, when you look at the other 2 top performing method, we can see that granularity plays a key role in performance, because if the method can find the right number of the module, it performs better. And these 2 two teams did a kind of recursive subdivision of the large network to a smaller group of the genes. And I forgot to mention that we had this constraint for the submission that basically we only consider a module valid if the size is between 3 and 100, because biologically it doesn't make sense to have a group of the genes more than having more than 100 genes. It's not possible for biology to kind of understand it. And going back to my introduction about how research is done, like WGCNA is a very well-known methodology for network clustering in biology. If you Google like a network-based modularization or network clustering or network analysis, this is the first you find. And it has R package, it's very well developed, but we had several groups that use this methodology and they were not in the top ranked methods. After getting all these results from the crowd, like all the prediction that we received from these 42 teams, we asked them if on top of that, we can leverage more from the wisdom of the crowd. So the idea was if we kind of integrate all the predicted module and build a new like a super predictor from this group of module, can we perform better or not? So we did that. We aggregated predicted module through a consensus metrics, where basically we measure similarity between the genes based on number of the teams that actually put these genes in the same module. So, and then we applied the top performing team on this new similarity metrics and checked how many of the group of the gene that we got are actually trait associated. And when we look at it, we get a good performance, better than the individual predictions, but not if we aggregate all the predictions. So here we played with the number of the teams that we put in our bag. Like first we started with all the prediction, and then we saw that okay, it doesn't work with having them all. But if we reduce the number of the team in our bag to 50% of the team from the leaderboard round, we got a good result, and it is better than individual prediction. If you remember, I mentioned that we had two sub-challenges. The second sub-challenge was about multi-network prediction. And we assumed that, okay, if we integrate network, we have a higher chance of having better prediction, because we are using more information, so it must be working even better. But unfortunately, it wasn't the case. So at the end, if we look at the ranking of the team and we compare it to the single like best team from the sub-challenge 1, which was a single network prediction, they can't, it's not that different. They don't really compare, and they didn't really beat the single network performance. And of course, the consensus also doesn't perform that well in the multi-network setting. And when we look back to the network, we saw that actually one of the reasons could be that this network don't overlap that much. So basically, the gene universe of this network have low overlap, so it's not all the genes in the same networks. That could be one reason behind it. We also looked at some properties of the predicted module, like similarity of them, how in terms of how similar they are in terms of having the same number of the genes in it. This is the kind of similarity of the predicted module in 2 dimensions, like their PCAs, the 2 PCs. We can see like the shapes is the network. The module come from which network, and the colors indicate that the module come from which method category. As you can see, the prediction are more close together if they come from the same network than from the same method. So basically, we can see that the network is more influential in the prediction than the method method category and method that was used for prediction. And We also compare the score that each team get to their average modularity of their prediction. So you might know that modularity is one of the most standard performance metrics that you would check if your method works well or not. But we can see that the top performing method of this challenge actually doesn't necessarily have highest modularity. So the most modular group of the prediction is not the best team. So it wasn't really the case for the result of this challenge. Also, if you look at the granularity of the results, we can see that not necessarily having a lot of prediction gives you the highest score in this challenge. So if you just randomly submit 1,000 of the group of the genes, it doesn't make you the winner. We had a wide range of traits predicted by these modules, and interesting thing here is that if you look at how many traits each module is associated with, we can see that most of the modules that were predicted is only associated with one trait. So if we compare the same thing with the genes, we can see like the percentage is lower. So it's kind of interesting to see that modularization gives you more precision towards studying the traits. So group of the genes are more trait specific than the group of the genes. So you have more specificity in that terms. And if we build a network from the modules that we got from the challenge and build this network from the prediction, basically each node is a category of the trait, and the connection between them shows that how many modules they have in common. And we can see that a module of similar trait category have more prediction in common. And of course, this was kind of validating the result, and it was interesting. But what a disease module really look like? Like when we say a trait module, disease module, what it is exactly? Basically, it's a group of the genes, and it has a high association to a particular trait, and in this case, height. And when we look at the single gene in this group, we see not all of the genes are really associated with this trait, like height. Only 3 of them. But this gives us like kind of list of the candidate for finding association between genes and the height. So if someone wants to study height, this could be the gene candidate for further investigation. And we validate this hypothesis by checking this association in a more recent a study that was more high power, so was able to capture more association between the genes and this trait. And from this newer study, we saw that actually most of the genes in this pathway are associated with height. This was my last slide about the result I got. And of course, this was a very big project. Many people and group were involved here, and I would like to thank them all, our group here, and IBM people and Vitality people and our top performer all together. And thank you for listening to my talk. And if you have any question, I'm happy to take.
We have like 5 minutes for questions.
So by when an individual will be able to find out his biosignature per se, depending on what he's deficient at?
How he's what?
I mean, there are individuals that develop or not disease, or prone or supposed to be early detected. This is for prevention.
Yes, yeah.
So by when someone like me will be able to find out who's like me?
Okay, with this study, for that you need really the whole genome sequencing. So we need really to sequence every candidate or everyone you want to check his risk of having a particular disease or not. But once you have his or her sequence, then you just need to look it up in the GWAS summary statistics or the gene score really. And if the person is the carrier of that variation, then it has a high risk of having this disease or problem. But for that, we need every patient sequence. So yeah.
So no forecast timeliness.
Yeah, we like forecast. Not really. You can't really forecast something that you don't have the information about it. So for a particular patient, you either need his genome to do it, or you need some background information about that person to do that. Yeah.
Maybe one more question. So what if one gene would be in several modules?
Okay, that's a good question. We actually didn't allow overlapping modules. So all these methodology that have been used here, they're all only predicting non-overlapping modules. So one gene can only be in one module.
We are a little bit constrained time,
Yeah.
so I propose you to go to ask Sarvenaz some more questions on the Apero. And I also encourage you to ask her about our ladies.
Yeah, I had a few slides about that, but I don't think we have time. Just very quickly, that's the Meetup to promoting programming and R programming, particularly for women, but it's open to all genders. So you are all welcome to come and participate in the talks and discussion and all activities we have. And thanks a lot again.